Welcome to Starstream, a new blockchain VM, and it's based off a reimagining of UTXO smart contracts based off first-party coroutines as a core primitive. Now, this video will be a technical introduction to Starstream. If you are not a developer and you're looking for more general overview of Starstream, we have a separate video for you, and you can find the link below. If you're a developer, you want to get more knowledge about Starstream and how to write Starstream smart contracts, this is the video for you. So the key insight to Starstream is that building a good system often is done by taking an idea to its logical conclusion. So for example, in Linux, everything's a file. In React, everything's a component. In Java, everything's an object. In Ethereum, everything's a smart contract. SQL, everything's a table, right? So in programming, taking one core concept and sticking to it often leads to a much easier program to develop and to understand, which often leads to success. And this is true not just in systems, but even true of games. So for example, if you think about League of Legends, for example, famously everything's programmed as in minions. Even when you're programming games, oftentimes it's kind of abstraction and sticking to an abstraction, even if it leads to weird bugs, can often allow you to outship the competition. So in this regard, Starstream decided to make everything a coroutine. So if you haven't heard of coroutine, we'll explain what they are in depth and exactly how you can think about these. But they might be related to other terms you might have heard of. So for example, delimited continuations or generators. But if you haven't heard of those, they're basically a generalization of async await that allow you to build your own scheduler. And we'll see exactly what that means. But before we get into that, what is a smart contract? So we're on the same page on this. So a smart contract is a deterministic state machine where state transitions are stored on chain, right? So in Solidity, the state machine basically looks something like this. And the problem with Solidity is that it has a global shared state, which often leads to bugs. It makes it hard to ZK-ify because they have to create ZK proof of the entire global state, and it hurts parallelism, which is why a lot of projects are achieving faster performance by moving away from the EVM model. And so you can think of the EVM as kind of a state machine with a single state for a contract, which is kind of the root of a lot of these problems. But what you often want is kind of a state machine with different states that are more local and easier to work with as opposed to one global state. And so the UTXO model kind of gives you this. It allows you to have different states at different times. And this is why you often hear people say like, oh, UTXO model is really great for ZK because it allows you to have more local states, and which allows you to have better parallelism and smaller proofs. But in practice, not a lot of people have used ZK for UTXOs. And we'll talk later in the slides about how Starstream basically solves this issue and they're able to have a very easy way to write UTXO-based smart contracts in a way that's ZK friendly. And we do this by basically adding a new field, which is the frame, aka the call stack, which is a kind of a coroutine concept. What does that actually mean? Like, that's super abstract. And I think it helps to go more to code concretely so you can get a good feel of the developer experience. But to get a good feel for developer experience, I first want to introduce some syntax so that when you see the code, you're like, oh, this is the syntax, this is what it means, I get it. So remember first async await, which you mentioned is kind of like a similar to coroutines. So async await is the most popular model for a pausable function. So for example, you have a here on the left-hand side, piece of JavaScript code that fetches Google and then fetches Reddit. So just fetching websites. And you have this kind of scheduler, which in JavaScript was the JavaScript event loop. You can think of it as kind of like the operating system that actually fetches the website for you and resumes your function once the fetching is complete. So JavaScript has this concept of generators, which, as we mentioned earlier, is related to coroutines. And it's a very similar syntax, right? So instead of async function, it's function star. And instead of await, it's yield. And the difference between async and generators in JavaScript is it allows you to have a custom scheduler. So you use await, async await, you're just letting the event loop be in charge of the scheduling. But when you're using generators in JavaScript, aka coroutines, you can write your own custom scheduler that chooses when to resume functions, how to resume functions, and so on. So you can kind of see an example of this where we're writing our own custom scheduler that first initializes our function, and it says, okay, run the next part of the function. It goes in, it gets google.com, comes in, handles it. And it says, okay, now give me the next part of the function. It goes in, calls it, resumes. Right, so it allows us to build our own custom scheduler. So let's see some other examples of this so you kind of get more of an intuition. So how would you write a JavaScript function that gives you an infinite series of numbers, right? So if you're not using async await or generators at all, it would look something like this. You have a function, every time you call it, it returns the next number. This requires an explicit global state we're trying to avoid. So here we're writing the same function, but now we have a generator instead. So you can see on the left-hand side, with my cursor over here, we first initialize the next ID to 0, and while true means this program runs forever, it always yields the next ID. And a custom scheduler basically initializes the function, and in JavaScript, when you do a for loop over a generator, it will automatically handle calling the next every time. So this will call the next, get the next number, and then print the console, which will print IDs forever. So you can see again another example of writing a custom scheduler instead of having to deal with async await. So note these generators don't have to be infinite, right? So you can yield 3 times and consume them 3 times to print 1, 2, 3. Okay, so now we have some background generators and we're familiar with kind of the core concept. The key insight is that these generators have 3 stages. The function definition, when it's not called yet, when they're running, and when the function is ended. And so the key insight, this maps very nicely onto UTXOs. So here on the left-hand side, we have our smart contract, which is our function definition. When you call the generator, you're initializing UTXO. And when the function returns, it's like spending the UTXO. Now we also have this concept of yield, which pauses the function until it gets called again, which is similar to finishing one UTXO and then creating a continuation, creating a new UTXO that represents the continuation. So it's super cool. We have this way of writing possible functions that actually, if you think about it, it's basically equivalent to the UTXO model. So what does that actually mean for writing dApps? Like, now we have this really cool insight. We have this really nice way of writing code, but how do we actually use code in this practice? And we're going to see different smart contracts using this new system. So first, let's look at how would you create a paid public key hash UTXO. So paid public key hash is so common in blockchains that oftentimes it's not a smart contract. So most UTXO-based blockchains, like for Cardano, for example, or Bitcoin, these are not smart contracts. They're just built into the blockchain itself. Let's imagine it was a smart contract. What would that look like? Okay, so you're saying that the user has some coins that they can only spend if they provide the right public key hash, so they own the private key. So basically, you look at the signatures provided by the user in this transaction. If the signature has the right public key hash, you return. Remember we said return ends the generator, aka spends the UTXO. So now we have a UTXO that can only be spent if the user has the right public key hash. If they have the wrong public key hash, we just fail the transaction. Okay, but so how do we write more complex things? Like, for example, a mint contract. So, for example, you want a contract that anybody can mint tokens forever. Well, now this is just a simple while loop, right? So you say while true, yep, you can mint. So this kind of infinite token is super easily representable by a few lines of code. And this extends, for example, to NFTs. For example, if you want the 10K NFT collection where anybody can mint, it's super simple. Now it's just a for loop. So you have 10K iterations of this for loop. It just says, yes, you can mint every time. But afterwards, the function ends and people can no longer mint. So if you're familiar with UTXO-based smart contract languages, you might notice that this is super, super simple. The equivalent contract in other programming languages like Icon is like 100 lines of code. And now we've got it down to 5 or 6 in a way that's super easy to read, super easy to write. So let's see some other examples of this. So for example, you want to have a really simple multi-sig. So this contract is not introducing new ideas, but it's another example to kind of build intuition before we introduce some more ideas. So multi-sig contract, well, it just lives forever. You never want your multi-sig to die. You initialize with some initial signers. While some people haven't signed the transaction yet, yield false, so there's still some people missing. And then now look at who has provided inputs to the transaction, removing the addresses that people have signed, and then just keep going. So keep going. More and more people sign the transaction, provide their signatures. Okay, everybody signs, and we yield true. The multi-sig accepts. We go back to the top, reinitialize, and then, okay, now we're ready to start making progress towards the next transaction. So, writing this kind of multi-sig is also pretty simple. Obviously, it's a very simple multi-sig. But you can see how you can write these contracts. Now let's introduce some more new concepts for you to look at. The first one is going to be contract composition, which is something that UTXO-based blockchains historically struggle with. So what if you want to compose multiple UTXOs together? Oftentimes what happens is that people split up the computation into multiple UTXOs. This is called transaction chaining. The problem is that not only does this lose atomicity, which you often want for DeFi specifically, It also makes it very hard from a developer's perspective. For example, a lot of wallets don't support this properly. A lot of explorers don't support this properly. A lot of tools don't support this properly. So it introduces a lot of complexity when you just want to chain stuff together in an atomic way. So to solve this in Starstream, we introduce this concept of a coordination script. So coordination scripts are stateless. They don't have state that lives forever on chain, rather just ephemeral construction. And the key thing is that these coordination scripts can iterate multiple UTXOs in a single transaction. So it's very different from, for example, Bitcoin or Cardano, where every transaction has one set of inputs and one set of outputs, and that's it. We're saying in Starstream, you could actually have a transaction, a coordination script, that iterates a UTXO multiple times. Right? So for example, we saw our NFT contract earlier, which had a 10K supply. What if we want to mint 10 NFTs? Well, that's just a for loop where 10 times we go into this mint function, right? In every loop, we consume a UTXO and create the next UTXO that's the continuation. So these coordination scripts allow you to do this transaction chaining, but all atomically, which is a new primitive we have in the Starstream VM. So let's see another example, which is oracles, which are historically also hard to do with UTXO-based smart contract languages. So note that oracles have two parts to them. One is providing the data, the other one is consuming the data. So providing the data is very easy. It's just the data, let's assume the data lives forever and we can reference it anytime. And whenever you call to this contract, it just gives you back the data. So super simple. The hard part is how to consume oracle data. The key insight is that in blockchains, UTXOs are kind of ordered, right? Blocks are ordered, transactions are ordered, therefore UTXOs are ordered. So this is UTXO 0, UTXO 1, 2, 3, 4, 5, 6, and so on. So we can give an order to the UTXOs that appear in the blockchain. And so that means that we can actually kind of think about iterating over UTXOs as just a for loop, right? Just like we saw earlier, we can iterate coroutines and generators just with a for loop construction. Now you'd be wondering, like, wait, that introduces issues. Like, that's not possible. Well, there's actually two issues, and we'll see how Starstream solves both of them. The first one is, of course, there's too many UTXOs to fit in a single transaction. So this is a common problem where, for example, the Oracle is just cranking out data, and then you as a dApp developer, you're trying to catch up, but there's just too many UTXOs. This problem introduces a lot of complexity in the dApp developer because now they have to handle this fact that you might have to do a partial update where you didn't iterate over all the data available. Starstream handles this very easily because remember that we said that processing UTXOs is already yield. It's already at this kind of pause point. So it makes it super easy to kind of continue from where we left off in transaction number 2. Because, we're already modeling things as possible functions. Therefore, in transaction 2, continuing off from where we pause, it does not require any new lines of code. So it makes it super easy to handle this Oracle problem. The second one is determinism. And we can solve this easily by just having that UTXOs can't reference their own ID. And so we can, in Starstream, easily avoid the two issues, which makes implementing oracles super easy in the Starstream model. And let's look at another common DeFi application, which is a DEX. And we'll see how the syntax we've introduced so far is not quite enough to implement a DEX. And we'll see how we can improve on this model to make DEXs super easy to write as well. So what is a DEX? Well, they usually have a liquidity pool. That's kind of the core concept of a DEX, which have some initial product, which is like kind of the Uniswap model of a DEX, an AMM. Let's say, okay, the AMM owes tokens to people. So initially, when you create the DEX in the first place, you don't owe any tokens to anybody. And then, okay, you wait for somebody to call the smart contract, to call the liquidity pool. The user provides you some value. If they gave token 1, give them token 2. If they gave you token 2, give them token 1. You might notice, like, wait a minute, this code is a bit wonky. It's hard to read. It's hard to write. Like, why are we yielding undefined? Why are we, like, killing the difference? And then instead of giving the user the tokens right away, we queue it and then, like, give them tokens later. And, like, what is the type of this function? Now there's, like, a undefined here. Like, what's going on? So this is, like, not great code. Right? So how can we update Starstream to make this super easy to read and to write? Well, before we get into it, let's think about the interface. Like, how do we want to use this DEX? Well, at a higher level, we want a kind of DEX coordination script. This coordination script takes in a user UTXO, and a liquidity pool UTXO. First, it yields the user's UTXO. Remember we said yielding UTXO is like consuming the user's UTXO. And we provide that the tokens to the liquidity pool, which gives back a tokens that their users owed, and then we kind of mint the UTXO that gives the user their tokens. So this is kind of like the high-level API that we like from the system. And so how we implement that is kind of like a high-level, like what kind of interface we want. We want to be able to provide a very clear type for a smart contract. We want to say like, okay, we have a DEX, it supports a swap function. The swap takes in a value and returns a value. And note that in the previous code, part of the reason we had all this complexity was because we actually commingling two different concepts. This function here handles the lifetime of the liquidity pool. It's like, okay, this liquidity pool lives forever. It also commingles, what does this smart contract do? Well, it handles swapping. So we've like combined two different concepts together into one function, which is why it's so ugly. So okay, you say, okay, let's split these concerns up. So we have some swap functions, so it's just thinking about the API. And now we have this create liquidity pool that just thinks about the lifetime. Remember, we said our lifetime is that it lives forever, liquidity pools never die. Okay, so now by splitting up the lifetime from the interface, we can now easily implement the swap function. The swap function says, okay, if you provide token 1, it gives you token 2. If you give token 2, it gives you token 1. So you can see by splitting up the lifetime and the API, we've made Starstream much easier to write, especially if you're familiar with Rust, because it's a very Rust-like syntax. But wait a minute, I thought we said Starstream is just coroutine. Like, what is this? This like Rust trade-like syntax flow is going on. To explain this, we're gonna have to think about something called effect handlers, sometimes called algebraic effect. So generators, as we saw previously in coroutines, are pausable functions. And effect handlers are resumable exceptions. Resumable exceptions, like what does that matter? Let's see that in detail. So what if you had a user program that throws an exception? So if you've ever written Java code, you've probably seen something like this. You have a function, it says, okay, my function can throw an exception, and then whenever you call this function, you have to catch. So it's super, super common Java code. And one thing is that we often have no way to recover from exceptions. That's not always true, right? There's some exceptions where you actually can recover. So for example, you might have a function that tries to allocate some memory, but it might throw an out of memory exception. In this case, there's actually a chance we might be able to recover, right? If you see an out of memory exception, you can maybe try freeing some cache and then saying resume. Okay, we'll try again. Now we free some memory, and maybe now we have enough memory to make some progress. So we actually want to be able to have this error that can resume. And note that now this is actually looking a lot like a previous slide. It's kind of like a generator, right? Where we try to do something on the left-hand side, then we have a scheduler, and the scheduler resumes back into the user code, right? It looks basically the same. And so the key insight here is that we can throw different exceptions in a function, and each exception can have its own type, right? So now we're saying we have an allocate memory exception and a free memory exception. And instead of trying to allocate memory, we just throw it right away. So we say, okay, whenever you want to have memory, just throw an allocate memory exception. And then on the right-hand side, you try to call the function, and it says, okay, catch. Or whenever the user tries to allocate memory, allocate the memory, and then resume. Okay, we go back with some stuff, and then, okay, we're done the function, so we free the memory, which gets caught by the memory scheduler. The memory scheduler frees the memory, and then resumes. So the key insight is now we're kind of hijacking this concept of reasonable exceptions to have generators, but with different type signatures. Right? Allocate memory takes memory and size and returns memory. Free memory takes memory and returns void. So through hijacking the exception system, we're able to have different yields with different type signatures. So notably, there's a language called effect if you're kind of more on the theoretical side of things and you want to see like languages that lean heavily into the system. The reason I mentioned that is because we're going to borrow some syntax from them. So instead of calling things exceptions, they call them effects. Instead of throws, they use the slash notation. Instead of throws here, they use raise. And instead of cache, they use with. So we're just going to be borrowing some syntax from them, which is why I talked about them. Okay, so now going back to our previous DEX contract, let's think about this in terms of effect. So this is one of the harder slides in the presentation, so just think about it for a second. But this is actually just syntactic sugar for this, right? We're saying, okay, we have a DEX coordination contract. When the user wants to swap, what a swap is actually doing is it raises an exception, which interrupts the lifetime of the liquidity pool contract. That exception gets caught, which then proceeds to do the swap, and then resumes back into the lifetime function. So the key insight here is that actually we can use this concept of exceptions to implement function calls into our system while still having everything just be coroutines. So function calls are actually just coroutines under the hood. And so just as a slight cleanup note, we're going to change away from this function star notation we had before, and we're going to call these main. So cool, now with this concept of effect handlers, we're able to have functions that have the lifetime and the API as two separate code blocks, while still under the hood actually just being coroutines. It's just a single core concept. And so maybe we can now revisit our minting contract, right? So remember, our minting contract was a 10k NFT. We can mint 10k times. This kind of concept of leveraging effect handlers gives us a very clean way to do introspection, right? Now we can have like a supply function that gives you the supply of your NFT, which just returns the supply variable, right? So this gives us a very clean way to do introspection about the state of local variables in our function. And we're wondering, like, what happens if supply isn't initialized? How can you just reference this variable like in a separate place? So to handle this, we're gonna introduce this new concept of a storage block. And the Starstream compiler will ensure that any variable specified in the storage block has to be initialized before the first yield point. That way, now we know that, okay, we can safely reference the supply variable inside these functions. Note that also this makes read-only UTXOs super easy, because now we can say, okay, this is just a function that takes in a reference, so it doesn't actually need to spend this UTXO. So it gives us a clean way to do this introspection this way as well. This also gives us, a fairly easy way to do like concurrent dexes, where we can say, okay, how do concurrent dexes work? It works by splitting up the ordered contracts from the liquidity pool itself. So this is how a lot of dexes work in UTXO-based blockchains. So people will queue up orders to be processed, and now we just, as a for loop, process all the UTXOs that are queued up. And so it's kind of taking ideas from the Oracle and taking some of the ideas from, our DEX example to combine them together to build a concurrent DEX. So what about shared context? How do you handle shared context in this new Starstream system? So for example, you might want to have a game. In the game, you have an inventory system. In this inventory system, you might have some kind of capture card where you can capture monsters. How do we enforce that you can only capture a monster if you're in a battle, and you can only capture the specific monster you're battling, right? So this is kind of like cross-contract dependencies. So how do we capture this kind of concept? Well, if you're familiar with concepts like React, you know there's kind of two ways to pass data around. One is the top-down approach, which you have a parent that's providing data down to its children. There's this other concept that's kind of bottom-up, which is called a context API. So you provide some kind of interface at the top, and then children objects can kind of reference this context from above. And we use this concept in Starstream to handle cross-contract dependencies. So notably, we have this kind of concept of effects in Starstream. And your function can raise an effect. It's like, okay, go up to the parent, go up to the coordination script, and say, okay, I want you to give me your address. So the coordination script's in a battle. If the user tries to use a capture card, then it goes in here, gets the caller's address, and so we can say, okay, you can only use a capture card if you're called from the battle script and you're in a battle, and so on. So it allows you to have this cross-contract system just by modeling effects that can go up and down the stack. There's some note about ZK, specifically about avoiding double proofs. If you don't know about ZK, you don't have to think about this too much. I basically want to avoid proving the same thing twice. And so the key thing is that in ZK solutions, we can think of this as basically embedding the answer of one side as a witness in the other. And so you can see this technique being used fairly often in different ZK systems. So for example, Mina, which is a ZK-based blockchain, where division is implemented as kind of like an inverse. So division is expensive in ZK, multiplication is cheap. So how do you define division? Well, you can just assume that you divide in vanilla JS, and then the ZK side, you just prove the inverse. So in Starstream, you can do something similar with kind of like raising an external request, like, oh, compute this function outside of Starstream, and then do the inverse. So I know for a lot of people who are not in ZK, like, this might be kind of confusing. You don't have to think about it. I just want to point this out for like the ZK people that might be watching this video. Notably, the reason I really want to emphasize this point in the ZK context is that it makes running Starstream in a parallel way, really taking advantage of UTXO, is super easy. Because what we can do is you can run the program in a non-ZK setting, because it's a deterministic execution. So first, let's run in non-ZK to know the expected execution. Then we can generate the ZK proofs of the coordination scripts, where we just assume the UTXO script results are witnesses. And then you can generate the ZK proof of the UTXO script, assuming the coordination script results are just witnesses. And all we really need is the final proof that checks the transitions between step 2 and step 3. And if you're really into ZK, you might know that we can do this with basically a memory consistency check, which we'll talk about later in a future slide. So now that we're done this kind of tangent for the ZK people, let's think about the type system for Starstream. So one of the cool things about Starstream is that we can think about the on-chain types of coroutine, right? So for example, some types we might care about is like events. So in Ethereum, for example, in EVM, there's a concept of events. Well, events are also just effect handlers that are caught by the core Starstream scheduler. You also have like errors, like you might want a transaction to fail. And errors are also just effect handlers that uncaught cause the transaction to fail. So you can see how all these different concepts, contract call, contract composition, events, errors, interfaces, they're all just kind of coroutines, and we can model them through a single core concept, which is how we've made, Starstream be such a simplistic VM. And so because of this, because it's such a simple concept, we can fairly easily reason about the types of things on chain. So what is the type of this contract? Well, you can just specify an ABI for your contract that says, okay, my contract has some event, has some errors, and some main function. And so we can easily say, okay, well, this contract is just some UTXO with some specific API that lives at a specific address. So why do we care about the type system? Well, we care about it especially in the context of tokens. So how do tokens work on Starstream? Well, here's kind of like the really cool idea. So remember in Starstream, we model UTXOs as just generators, as coroutines, right? We model the lifetime of the function as a coroutine. But tokens also have a lifetime, right? A token starts when it's minted and ends when burns. So the key insight is, what if we also represent tokens as generators? So notably, for example, if you look at a lot of UTXO-based blockchains, their UTXOs look something like this, where they have a bunch of fields and they have some kind of value type with different tokens inside the UTXO. And you can think of these tokens as basically just being a generator with 2 entries in storage, the amount of the token ID. In a lot of cases, the lifetime is just, live forever kind of thing. So value really is just the generator that wraps other generators, right? But we do have a bit of complexity here, because how do you now think about composing UTXOs? Like, what if you have a UTXO that contains other UTXOs inside it? Like we talked about this, like this is kind of like a wrapper, right? How do you think about this in the concept of like lifetime, right? Right. If my contract here accepts a UTXO and my contract ends, what happens to the UTXO I accepted? So we have to think about this as kind of a generalization of other blockchains. So in other blockchain, when a UTXO dies, it releases all its tokens, and the blockchain forces that transactions must be balanced. So for example, if you have a transaction which has 5 Bitcoins as inputs, you must have 5 Bitcoins as output minus the fee, right? So you have to make sure the transaction is balanced. So Starstream, we generalize this idea. Instead, say that when a generator dies, when this function ends, it releases all its subgenerators, aka tokens. And instead transaction must be balanced, it's basically generators must be linear types. So what does that actually mean? So linear types are types that you can only use once, and exactly once. A similar concept is affine types, which are types that you can use 0 or 1. So we use linear types to represent intermediate values in Starstream, and affine types are used to represent persistent values. So let's think back to our pay to public key hash example. When we use this pay to public key hash and coordination script, the user UTXO is non-error, because remember, UTXOs can be iterated and potentially live forever. So we can use it once, we can use it 0 times, we can use it 2 times, doesn't really matter. This is not an error. It's an affine type. It's a persistent thing that lives on chain. However, consuming user UTXO might release some token, and we have to handle the token. If there's 5 Bitcoin input, there must be 5 Bitcoin output. Similarly, if you consume a UTXO, you must handle the outputs of that UTXO. And so this is a compiler error, because transactions returned from this contract call cannot just disappear. It's a linear type. So we still have this, this solves the lifetime issue, but we still have this kind of complexity, which is, what if you have UTXOs of UTXOs of UTXOs of UTXOs of UTXOs? This is really hard to reason about from a developer's perspective, because, okay, here you say, okay, I freed, I iterated UTXO, I released some tokens, but those tokens could also release tokens. It just ends up with an infinite loop of always potentially releasing tokens. So we want to, avoid this kind of we want to avoid this Russian doll of UTXOs, UTXOs. How do we simplify this? So we introduced 3 rules, which help constrain this. The first one is that UTXOs cannot be nested at all. There's just no nesting. Instead, values, aka tokens, are transferred through an intermediate type. So to make this not have a huge performance hit, tokens must have a low overhead serialization and deserialization. And tokens must expose 4 functions: a bind and an unbind function that basically converts this intermediate type into something owned by UTXO, and converts a token owned by UTXO into intermediate type. So this is saying basically, okay, I have, 2 of a token, and these 2 tokens are now owned by this UTXO. So UTXOs can have many tokens inside it, like we saw earlier. This value type is like a wrapper, right? So bind, unbind define wrapping and unwrapping tokens. And then mint and burn create a token and delete a token. Notably, it replaces main, and it works basically similar to the main, except we introduce this concept where they're forced to have low overhead, aka they cannot have local variables that are persisted. So let's look at this kind of in practice. So we have a API for our token, the storage for our token, the mint for our token, the burn for our token, the bind, and the unbind. And the left-hand side is just syntactic sugar for something that looks something like this on the right-hand side. So why is this token concept so powerful? Well, first of all, it's pretty cool because we're now able to build tokens just with coroutines. We don't need to introduce a new concept. It's, again, just coroutines. But remember, we talked about how the types of Starstream are so simple, it's really easy to implement on-chain. That's pretty cool because we can say, okay, here's our pay to public key hash smart contract. So remember, this is our pay to public key hash smart contract. We can say, okay, what tokens can this pay to public key hash contract accept? Well, let's just say it can accept any token, any type of token. Okay? And when you initialize the pay to public key hash, you're saying, okay, the pay to public key hash is locked by some hash, and also will own some tokens. And then we bind all these tokens to this UTXO. And then when our function returns, this implicitly unbinds all the all the tokens from this UTXO. So the fact that we can restrict which tokens our UTXO can hold is pretty cool, but it actually is more powerful than you might think, because effects plus explicit types actually allows for permissioned tokens, right? So we can limit the tokens our contract can handles, and bind and unbind can actually throw effects. Remember, we saw earlier that bind and unbind are just regular functions, and functions can throw effects in Starstream. And we can use this concept to specify permission tokens. So for example, you can say, okay, pay public hash, it can accept any token, just uses any. But if you wanted a liquidity pool that can only accept non-permission tokens, well, you could say, okay, my liquidity pool accepts any token with no effects and no errors. But maybe you want to build an NFT marketplace that only accepts tokens that enforce royalties. So you can say, okay, my NFT marketplace accepts any token, but it has to have this get royalty effect. Whereas this concept of having effects that tokens can have and being able to enforce on-chain how these effects are handled allows us to have these permission tokens, like enforce royalties and stable coins and soulbound tokens and all these kinds of things that are historically hard to get on UTXO, but in Starstream, they're super simple. Now, finally, let's talk about ZK a bit more. So ZK, like, what do we care about ZK? Well, ZK actually gives us two things that are super important. It gives us compression. Notably, in Starstream, we're able to compress batches of transactions in just 16 kilobytes, which, for example, in Cardano is the size of approximately 2 transactions. This is great for real-world assets because real-world assets often have things like, okay, we want to track the progress of a wine bottle that goes from city to city to city. If you had to track every single wine bottle on chain, this would be a massive amount of data. It's just too much data. But in Starstream, you can trace the history of this wine bottle, which is a token. It's updating. And you can compress that entire history in just 16 kilobytes. So it's great for real-world assets. It's also great for DeFi because, as we saw earlier, in DeFi, you often have different things you want to chain together. First I want to swap a token on DEX. Then I want to provide, some token to a lending protocol, and then get the asset I got from that, and provide, a swap on another of the DEX. Right? There's oftentimes in DeFi you want to keep chaining things together. In Starstream, you can not only easily model this kind of chaining of things, we can also compress all of it into a single transaction, 16 kilobytes, as the entire chain all atomically. It's also great for gaming because in gaming, you have users doing a massive amount of actions. For example, they're playing an RPG, they're attacking monsters, they're moving on the map, they're doing a whole bunch of stuff. You can't put every single action on chain; it's just too much data. What you can do is you can have the user session be compressed together into a single ZK proof and submit that on chain. So compression is super important in ZK, but another important thing that you sometimes get in Starstream can give you is data protection. It allows you to have transactions without revealing private metadata. This is super important for real-world assets for regulation. For example, you might have some information like a credential where for regulatory purposes you can't actually put the information on chain, but you still want to have proofs of those statements. Like you want to prove that the person is over 18 or lives in the USA. So you want to have statements about that information without revealing the underlying information. So this privacy is great for real-world assets. It's also great for DeFi because it allows you to avoid front running, which is a common problem in different dexes. It's also great for gaming because in games you often want some kind of fog of war where you don't know what the opponent is doing. And so this kind of data protection that Starstream can give you through ZK is also really useful for a lot of new use cases that Starstream can enable. So notably, a very hot topic in ZK at the moment is something called IVC, incrementally verifiable computation. It's a cryptographic primitive for proving correctness of an iterated and incremental computation. So the really cool thing is that IVC can also just be a coroutine. Like we have this concept of an iterated possible computation we can move over time. And so this gives us a super easy way to ZKify a coroutine. And because in Starstream everything's just a coroutine, it means we get a very easy way to ZKify smart contracts, an easy way to ZKify tokens, ZKify transactions. Like everything is just so easy to ZKify in Starstream because of this nice abstraction. So like a very common ZKVM construction is you have a program. That program gets compiled, for example, to WASM or RISC-V. You have a proof of each step, and then you you combine those proofs together. And so this is called like a folding scheme. So there's many different ways to implement ZKVMs. This is one of the popular constructions. The key thing to know is that these constructions have basically two things they're proving. They're proving the opcode, but they're also proving the memory, right? If you do like A plus B equals C, A and B are like registers in memory, right? So you need to not only make sure like A plus B equals C is like right from a math perspective from the definition of addition, we also need like proof of like what is the content at memory A, what is the content of memory B, is that equal to the content of memory C? So you have to handle memory. Notably, this comes from a concept called memory consistency checks, or MCC. So the really cool thing about Starstream is we don't need to implement any new opcodes, right? We can take ZKVM for WASM or ZKVM for RISC-V or ZKVM for a different concept. It doesn't really matter. Starstream only requires new memory consistency checks on top of it. Because if we talked about, memory, UTXOs, tokens, they're just memory concepts on top of base VM, right? And so this gives Starstreams a lot of flexibility of the underlying ZKVM, which means that porting Starstream as new ZKVMs come out, as new improvements come out in the ZK space, it's super easy for us to upgrade Starstream and leverage the latest technology. And so one of the biggest problems with a lot of ZK projects is that they can't have a good upgrade path. They're stuck on an old cryptography, and ZK is moving really fast, and they're stuck on old tech, and then they die because they can't upgrade. Because of the way Starstream is developed, it gives us a very easy way to update the underlying VM without having to change Starstream concept, which I think is really cool and allows Starstream to stay competitive going forward. So as you see, Starstream is a really powerful concept, and it could end up being a common VM for a lot of different chains. Of course, one of my personal interests is UTXO-based blockchains like Cardano, where I think it's a very natural fit. You could also look at ZK-based chains like Midnight or Mina. You could look at chains that are based off a common ISA, like Arbitrum that uses WASM, or Substrate that uses WASM, or recently RISC-V. Or you could think about use case specific constructions like Pima, which is like made for gaming, or layer 2s in general, where there's a lot of like app specific layer 2s. And I'm sure there's other things as well. And so you might be wondering, well, okay, this is super cool, but is this real? And actually, it is real. In fact, we have the code on GitHub. We have some proof of concepts, for example, the tokens, and the batching, and the browser support. We're still working on some stuff like the ZK, but we have a working group on Discord for this, and we have 50 people in the working group already with 22 different companies interested in either using Starstream or contributing to Starstream, and you're welcome to join that Discord as well. Notably, we have a QR code you can see on your screen as your way to join our Discord. And if you can think of Starstream kind of like an alternative to Plutus or EVM or these kinds of blockchain VMs, and we're building this as a public good. That's to say, we're building Starstream for now, but anybody can contribute and anybody can use Starstream. So if you're interested in Starstream for your project, definitely reach out to us or just look at the code on GitHub and just go for it. It's yours as much as it is ours. MIT and Apache 2 license. So hopefully through this presentation, you've got a good technical understanding of Starstream. If you want a higher level understanding, remember as I mentioned at the start of this video, we have a more like high level overview of Starstream as a separate video. But I'm super excited about the work we've been doing at Starstream and super excited to finally announce this to the public. And it's going to move super fast. So I'm super happy to be on this journey with all of you.